In this video, we're going to discuss the basic behind neural networks. We're going to see a few examples on how neural networks can be implemented and why they are important. And also, we're going to briefly demonstrate how we can learn the parameters of neural networks from our data. So we will start with the basic unit of a neural network, which is called the perceptron. And the perceptron is represented in a very similar way that we have seen as part of the logistic regression algorithm. So the perceptron takes as an input a set of d-dimensional features and multiplies each of these features with a certain weight plus a bias term, and then passes this linear combination of features through the sigmoid function or any other type of activation function. In this way, in this case, we use the sigmoid function, which is the easiest and the most widely implementable. And the output of this sigmoid function is the output of our linear, our perceptron unit. So this, as we have seen in the case of logistic regression, can be used for classification purposes. So for example, if the output of the sigmoid function is greater than 0.5, then we can assume that the input sample belongs to class 1. Otherwise, we can assume that the input sample belongs to the negative class. So beyond the one-dimensional output, we can also have output of multiple dimensions. And in this case, we see a k-dimensional output, which can correspond to k different classes. And instead of using the original sigmoid function, we use this softmax function, which is a generalized version of the sigmoid function, which is the same thing that we have seen in the multi-class logistic regression. So again, in the case of multiple classes, the output of each class is represented by the inner product between an input and a set of weights that correspond to that specific class, which is passed via this softmax function. And we can conduct a 0-1 encoding or a one-hot encoding for the output vector in order to represent the output labels. So how do we train this case of the basic linear perceptron unit? We can use gradient descent or stochastic gradient descent, which is actually faster. The evaluation metric that we use in order to optimize the weights of the perceptron is the cross-entropy function. The cross-entropy function, as we have seen it so far for a single training sample, is basically this definition here, which is essentially the negative logarithm of the likelihood of the logistic regression algorithm. And this is the same cross-entropy function for the multi-class logistic regression. So when we perform the optimization through stochastic gradient descent, we update each of the weights of our logistic regression in a proportional way to the input sample multiplied proportional to the error. So some advantages related to this training of the perceptron algorithm is that it is cost efficient, both computationally and memory-wise, because we assume a single sample per update or a subset of all our training data. It's also effective since it can adapt over time if the nature of our training data changes over time. Also, the error function is quite interpretable because it is expressed in terms of the error of individual functions, of individual samples. Therefore, this can be quite interpretable in performing data exploration and understanding which of the data are not potentially correctly classified. And another good thing about the stochastic gradient descent in the case of perceptron is that we can get some weight estimates even after a small number of iterations, even after a single instance has been seen. So here are a few examples of linearly separable problems in which a linear perceptron can be used in order to solve them. So this is an example that quantifies data from a Boolean AND function. In the case of Boolean AND, if we have a two-dimensional input, we have 4 different cases, which can be represented by the 4 different samples that are being depicted in this table. The first 2 columns of this table represent the two-dimensional input space, and the last column represents the class output, which is the result of the Boolean AND. So we can see that when either of the 2 input variables are 0, then the result is 0. Otherwise, if both input variables are 1, then the result is 1. So the question here is, how can we use this perceptron unit in order to implement this Boolean AND function? And here is how these 4 samples are also being represented in this two-dimensional space, where essentially these 3 samples belong to the negative class, and this sample here belongs to the positive class. So the goal of the perceptron is to find a set of weights and a bias term that can implement this function and essentially find a line that separates these 3 samples based on the classes that they are assigned. We can see here that one potential combination of bias and weights is this combination here, when the bias equals to -1.5 and each of the weights equals to 1 for each of the 2 input samples. And if we select those parameters for the perceptron unit, we can see that all 4 training samples are being correctly classified. Of note here, these parameters are not unique. We can find many other combinations of weights and bias terms that can also implement the same Boolean AND. So we can see that using this simple perceptron unit, we can actually implement this type of Boolean AND function. And the reason for that is that these 4 samples are linearly separable, meaning we can find a line that can correctly classify these 4 samples into the positive and the negative class. In a very similar way, we can also find samples we can also find a perceptron unit that successfully implements the Boolean OR function. So the Boolean OR function, again, has 4 different cases, therefore can be represented by 4 different data samples. If one of these data samples has an input 0 and the other has an input of 1, this Boolean OR, if both the input samples have an input of 0, then this Boolean OR is 0. Otherwise, the result is 1. And there is a small typo here. This result, when x1 equals 1 and x2 equals 1, this result is 1. So we can understand that we can find another example of a linear perceptron which can implement a Boolean OR function. And in this example, we can find a bias term that is equal to -0.5 and the weight terms that are equal to 1 and 1 that can also correctly classify those 4 samples. However, we can see that if we have linearly non-separable cases, such as the case of this XOR function, then there is no perceptron unit or there is no line that can correctly classify these 4 samples. In the case of the Boolean XOR, if both variables have the same value, then the result is 1. Otherwise, then the result is 0. Otherwise, the result is 1. So we can see that Boolean XOR results in data spaces that look like this, where there is no line that can correctly separate these 4 samples into the 2 assigned classes. And what I meant by this is that there is no single line that can represent those 4 samples. However, instead of having a single line, which corresponds to a perceptron unit, we can have a combination of perceptron units. So here we see that instead of using a single perceptron, we can use 3 different perceptron units. And with these 3 different perceptron units, in the first 2, we can get some type of linear combinations of the input sample for each of these 2 units. And then these units can be also combined with another combination that gives the final output of the XOR function. And if we assign some weights, if we look a little bit, if we try a few weight combinations and assign some weights to these parameters of this combination of perceptron units, we will see that we can find actually some weights which can successfully classify these 4 non-linearly separable samples. So this is the whole intuition behind using a set of perceptron units in order to implement non-linear transformations of the input space. And this is particularly helpful when we have non-linearly separable data, which many times is the case. So moving forward, we're going to see how can we use this basic perceptron unit in order to represent a neural network, a feed-forward neural network, or otherwise called multi-layer perceptron. So multi-layer perceptron is a type of feed-forward neural network that can model nonlinear associations between a d-dimensional input space and the output. And the multi-layer perceptron is implemented by the multi-level combination of many perceptrons. So in this case, we can see a multi-layer perceptron that has one input layer, the output layer, and also one intermediate layer or one hidden layer, as we call this type of layer. We can see that this perceptron has 3 input features. The hidden layer has 3 nodes, and the output layer has a single output that is being represented by a single node. We can also see that each of the 3 inputs of the multi-layer perceptron is connected with all the nodes of the hidden layer. And each of these weights is different. So this means that input X1 is connected with a given weight to the first hidden node, but also to a different weight with the second hidden node and a different weight with the third hidden node. And the reason for that is because we are trying to have different types of representations as a result of each of these hidden nodes. If each of these input features was connected with the same weight to each of these hidden nodes, then this would result in exactly the same representation in each of the outputs of each of these hidden nodes. Therefore, this would really defeat the purpose of this multi-level combination. Similarly now, once we have represented each of these hidden nodes, then each of these is being connected with the output with another set of weights. Now, from this qualitative description, we can also provide a more computational description of the multi-layer perceptron, of the representation of the multi-layer perceptron. And as part of this computational description, we have our input features, in this case, X1 through X3. And we have the weights that are being represented by the weight vector W, the weight variables W. So weight Ij is the weight that connects unit J of layer L to unit I of layer L+1. So this means that if we have the first layer, the input layer here, and the second layer, the first hidden layer here, then we use weight W11 to connect the first input with the first hidden node. Similarly, we use weight W12 to connect the second input with the first hidden node, and so forth and so on. We can see that the output of the first hidden node is being represented as the linear combination of the inputs x1 through x3, each multiplied with the weights W11, W12, and W13. And these are essentially being represented by these arrows. This arrow here, this arrow here, and this arrow here. Of course, we also have a bias term, because the bias term is also essential in order to account for the range of the input features. And all this combination right now is being passed through a nonlinear activation function, this function f as we call it. So for all practical purposes, for the multi-layer perceptron, we are going to assume that this activation function is represented by a sigmoid function. But moving forward, we are going to see how this activation function can be different, especially when we have neural networks with multiple layers. Now, similarly, if we want to represent the output of the second hidden node, again, it's a combination, another linear combination of the input features, which is represented by these different weights, W21, W22, and W23. And we can also note that in these notations, we have also this exponent 1 that represents those weights. So this exponent is basically quantifies the weights that connect the first input to the second layer of the neural network. Now, if we want to represent the connections between the second and the third layer of the neural network, essentially the hidden layer and the output layer in our case, we are going to use this exponent 2 for the weights. So in a very similar manner now, if we want to represent the output of the neural network, we have to connect all these different nodes of the first hidden layer. And in this case, this is the only hidden layer. So we're going to use those weights, W11, W12, and W13, with an exponent of 2, because these are the weights that connect the second layer with the third layer of the network. And these weights are being represented by these 3 arrows right here. Again, if we perform a classification task, we have to pass this linear combination through a sigmoid function if we perform a binary classification task, in order to ensure that the output represents some type of probability of our sample belonging to the positive class. So in terms of more terminology, in neural networks, the output of a hidden layer is called the activation. And of course, we also have the weight and the bias term, which are being represented in the same way that we have learned in all the other classifiers that we have seen so far. So this procedure is called forward propagation because it captures the progress of propagating the input of our space to the output, in this case, to the classification outcome. And this propagation is being done by layering multiple nodes, multiple perceptron units, and then combining each of these perceptron units via different weights and via the activation function. We can see that instead of having these more extensive notations, we can also represent each of these vectors, each of these single variables, by a matrix and a vector. So we can have the matrix of our weights and the vector of our bias terms. Here, this matrix W1 corresponds the matrix of all the different weights that connect all the inputs with the first hidden layer of this neural network. And similarly, this bias term, this bias vector connects, basically helps implement the linear combination in each of these nodes of the first hidden layer. Now, beyond having a single hidden layer, we can also have multiple hidden layers. So in this case, we see a multi-layer perceptron with two hidden layers, basically this layer here and this layer here. And this also, of course, has an input layer and the output layer. We can also see that instead of having a single output, we can have multiple outputs. So these outputs can be different classes, or sometimes instead of implementing classification, we can actually implement regression in our neural networks. This would translate into not having an activation function at the output layer. So in this case, because the regression task would mean that we would have an output most probably in the real numbers, in the space of the real numbers, therefore we would not need an activation function as an output in this layer. So far we have seen the representation of the multi-layer perceptron, and the big advantage about using these multi-layer perceptrons is that we can implement non-linear classification functions, which means that if we have, for example, non-linear spaces, such as in this example of this non-linear space, or in this example of this non-linear space that we see here, we can actually have a set of hidden layers that can help us implement these non-linear classifications. That can help us capture these non-linear input spaces. Now, just a simple question of basic understanding here is how many parameters does this neural network have? So in this neural network, we have an input layer with 3 features. We have a single hidden layer with 4 nodes, and we have an output layer with 2 different outputs. We can see that the input layer with the hidden layer is being connected by a number of weights, which can be said to be 3 times 4, because each of the inputs is being connected with this node of a hidden, with a node of the hidden layer with different weights. So 3 times 4, this means 12 weights. Similarly, the hidden layer with the output is connected with 4 times 2 equals 8 weights. Now, the question here is if this is enough, or we might have missed something. And we have actually missed here the bias terms. So beyond the actual weights, which are these 20 weights that we just described, we also have bias terms every time we implement this linear combination of features that is passed through this nonlinear activation function. So here we have each 1 weight per hidden layer, so 4 weights that are being connected in each of these units, and 2 weights, 2 bias terms, sorry, that are being connected in these units. So this results in 20 weights and 6 bias terms, therefore a total of 26 parameters. This video has basically discussed so far the representation of the multi-layer perceptron and its basic unit, which is the single perceptron. The question here is now, how can we learn the weights of the multi-layer perceptron? And the way to do this is through a method that is called backpropagation. So backpropagation is essentially a generalization of the gradient descent method that we have seen so far. We're going to first describe the criterion that can be used in either a regression case or a classification case in order to optimize the weights and basically learn the weights of the networks via backpropagation. So if we have a regression case, the criterion that can be used is the RSS error, meaning how much the output of our network is different from the actual label. And here the output of the network can be represented via this function h, which depends on the weights. These are all the weights of the network and on all the bias terms of the network. In the same case, if we have a classification function, then the criterion that needs to be optimized, or in this case, minimized, is the cross entropy error, which is similar, exactly the same concept of the cross entropy error that we have seen in the case of the logistic regression. Beyond that, we can also apply regularization in all these methods. And now, because we have a very, essentially, the more units we add, the more these weights are being added exponentially into our problem, we can add these regularization terms in order to make sure that the networks do not overfit. So this function corresponds to the regularized version of the regression implemented by a multilayer perceptron. In this case, of course, it is a nonlinear regression, as we discussed, because each of the hidden layers basically has some type of nonlinear activation function. So in this case, we have basically our RSS error, and this is added to the regularization term. In this case, we have an L to norm regularization for all the weights. Similarly, we can have the cross entropy error and an L to norm regularization for all the weights as well. How are we going now to optimize these functions in order to find the weights of the neural network? We're going to perform essentially a gradient descent operation, but instead of performing a gradient descent operation on only a single layer, we are going to successively perform gradient descent operations over multiple layers of the network. So the basic update rule remains the same as the update rule that we have seen in the basic version of gradient descent. So essentially, the weight is being updated based on its previous value on the previous iteration minus a learning rate times the first order derivative of our optimization cost with respect to any of these weights. However, the problem here is that each of these weights is not necessarily visible by the output of the algorithm, meaning these weights can be weights of the output layer or can be weights of each of the intermediate hidden layers of the network. For this reason, what backpropagation does is that for each node and each layer, it computes an error term. It uses that error term in order to update the weights of that specific layer, and then it backpropagates this error in order to compute the intermediate error of the intermediate layer that it is right before that specific layer. In that point, it uses this intermediate error term in order to update the weights of that layer, and then it keeps backpropagating the error and updating the weights of the other layers. If we were to show this schematically here, this would mean that as part of this backpropagation process, we would estimate the errors here at the output layer. We would update the errors, we would update the weights at this output layer based on this update rule here. So the first order derivative of the weights at the output layer is proportional to the error at the output layer and the activation at this output layer. And what we would do is that we would backpropagate these delta errors onto the first hidden layer. And this backpropagation would happen through this definition here. So the weight on the previous hidden layer, these weights here, are a linear combination of the weight at the output layer multiplied by the learned weights. And here multiplied also by the first order derivative of the activation function. Once we have computed the errors at the intermediate layer, what we do is that again, we recompute the weights now that connect the input layer with the first hidden layer. And these updates again are being performed via this update rule, meaning by computing again the first order derivative of the optimization function with respect to each of these specific weights. In the next video, we're going to provide an example, and we're going to actually work through this specific case in order to understand exactly how this backpropagation method works. So this is the end of the video that discusses the representation of the multilayer perceptron and an outline of how we can train the weights of the multilayer perceptron. In the next video, we're going to show an example of the backpropagation process.